Hi guys, in the last video we were able to derive the initial condition equations and circuits for both capacitors and inductors. So now we're going to directly use what we learned from that to solve two circuit theory problems with the Laplace transform given initial conditions. So let's get to work. Assume that Vs of t equals 10u of t, as the initial voltage here is 10u of t volts, and that at t equals 0, minus 1 amps flows to the inductor modeled as a current source, and 5 volts flows to the capacitor modeled as a voltage source. So we kind of have an assistance here, because they already told us to model, not really an assistance, it's more of a strict way of doing this now, because usually you'll be able to choose between modeling both of these as either current sources or voltage sources, right? But this question told us that inductor has to be modeled as a current source, so that means the inductor is going to be in parallel with the current source going this way, and it has to be, or you won't get the question correctly. And your capacitor has to be modeled as a voltage source. It has to be. Ideally, you should be able to choose, but since this question is strict, we have to do as we're told. So minus 1 amp flows to the inductor modeled as a current source. So to prevent this minus sign from confusing you, just draw your currents as you would flowing down, right? And call this minus 1 amps and solve it naturally, so you don't get lost with the signage and everything. And 5 volts flows to, or that's probably voltage across. So V naught for the, okay. So voltage across the capacitor at t equals 0 is 5 volts. And the current to the inductor at t equals 0 is minus 1 amps. So these are the two crucial things that we're going to use to solve the circuits. And they were given exactly how to model. So let's get straight to business. Now we're given initial conditions. So our circuit our circuit in the S domain is going to have more elements. Okay, so usually we'll start with our voltage source is 10 of t. Draw voltage source. Then our resistor 10/3 ohms. Okay, we have our inductor 5 henries, and we're told to model this guy as a current source. Okay, so when modeling inductors as a current source, let's say this is your time domain, this is your inductor. We covered this in the previous video, L I of t. Okay, call this V. As a current source, you're going to have your inductor in parallel with the current source leaving the node, so going downwards. These are going to have an impedance of SL, and the value of this is going to be I0/S. Verified. Yes, that's going to be I0/S. So this is voltage as a function of S, and this is current as a function of S. So this is what we're going to do since we're modeling this guy as a current source. We already know I0 to be 5. I0 is minus 1 amps. Okay. And V0, I'm assuming, was 5 volts. Right? That's correct. Okay, so we have our inductor SL. So that's S times 5. So that's 5S. This is 10/3. Resistors stay the same value. Our VSU of t, let's make this better. Gotcha. Our VSU of t is 10 u of t. That's the unit step function. So that's going to be straight up 10/S without any issues. So we need to draw a current source in parallel with this guy, leaving the node. The direction is very important. And the value of this is I0/S. So that's going to be simple and straight minus 1/S. Leave it as that. What you're given, put that as the value of the source. No adding, no questioning. Then our capacitor is being modeled as a voltage source. Okay, so that's plus minus. So this is for inductor. Then for modeling capacitors as voltage sources, it's usually BC. It should be V of t, I of t. I think I'll link the previous video at the top or in the description so we can see exactly how we got these formulas. So modeling the capacitor as a voltage source is going to be in series. This will have an impedance of 1 over SC usually, and the voltage of this new model source is going to be V0 over S. Okay, this is voltage as a function of complex variable, current as a function of complex variable. So that's exactly what we're going to do here. We're given 0.1 farad, so that's 1 over 10 farads, and the impedance of this is 1 over SC together. So that's to be taking this up, so that's 10 over S. 10 over S, and this is going to be V0, since V0 is 5 over S, so that's 5 over S volts. Okay, so you can now call this your S domain equivalence. So these are the steps you need to do to start solving. First thing you have to do is, since we're given initial conditions, you can decide or choose how you want to model each one. But since we're given precisely what to do in our circuits, there's no freedom of choice with that one. So we're going to straight up jump into solving this as we would with normal circuits in the time domain. Okay. And the pro tip we can see here is that since we have a couple of elements in parallel, okay, you can see 1, 2, 3 in parallel, and this is simply a voltage source then a load, we can use nodal analysis, we can use KCL. So what we're going to do is now I'm going to analyze everything, analyze at this node. Okay, this is going to be ground, that's 0 volts. So, for if you have current entering an element, let's say this is our V0, this is our V1, this is of resistance R. Then the current through this, I through R, is going to be V0 minus V1 all over R, given that current is flowing from, V0 to Vi, because you're going to have a voltage drop across your load. So that's the basic principle of nodal analysis, which is what we're going to use to solve this question. Okay, first of all, set up our currents. We'll call this I1 entering the node, I2 leaving the node. So I1, I2. We already have the direction is down. Direction is always going to be down. Our value was 1 over S, so we're going to leave it as that. This I2. So I3 is also leaving the node. Okay, and I4 coming from these two guys is entering the node. Okay, simple and straight KCL tells us that I1 plus I4 is equal to I2 plus I3. Okay, everything we're going to do is going to be based off of this. So for I1, initial minus final. This entire node is going to be at V0. Okay, the entire node is going to be at V0. This node is going to be at 10 over S. This node down is going to be at 0, and this node here is going to be at 5 over S. Up and down 10. Okay, when we solve for I4, we'll see it. So we have for I1 10 over S minus V0, since we were going from initial to final, and our current is flowing from this source to V0. Then divided by, you're dividing the whole thing by the load of the current as across. So that's over 10 over 3. Okay. Plus, we're going to do the same thing for I4. Now we're going this way, taking current this way. So this first node, as meeting it, is 5 over S. Okay. 5 over S minus V0. All of this is going to be divided by the load of this 10 over S. Okay. This is going to equal I2 plus I3, simple and short. So for I2, this is ground. So this is 0 volts. And our current is flowing this way. So that's going to be V0 minus 0 over 5S. which is the same as V naught over 5s. V naught over 5s minus 1 over 5 minus 1 over s. Whoa. I have to be careful with that. So minus 1 over s, since our current is going this way. Okay, I can simplify this. So that's 3. 3 is going to come up. 3 into 10 over s minus V naught all over 10 plus s all into 5 over s minus V naught all over 10 again is going to equal V naught over 5s minus 1 over s. Okay, so let's see if we can multiply through by 10 to get rid of this denominator. Okay, so that's going to be 3 10 over s minus V naught plus s into 5 over s minus V naught is going to equal 2 V naught over s minus 10 over s. Okay, let's expand these guys. So that's 30 all over s minus 3 V naught plus 5 minus s V naught is going to equal 2 V naught over s minus 10 over s. Okay, I think the only thing we have to do is handle this fraction. So that's going to be 30 minus 3 s V naught all over s plus 5 minus s V naught is going to equal 2 V naught all over s minus 10. Let's multiply through by 10 minus 10 over s. So now we're going to multiply through by s. So the usual really expert advice you get when solving with Laplace transform is that you're always going to have a couple of denominators if you'll be using nodal analysis. So where you can, clear your denominators so you have to try and get closer to linear algebra as you can. As you see, once we came here, we cleared with 10. We would have actually done 10s here. Okay, but we cleared with 10 from here. And now we're seeing s is common below. We're going to multiply everything through by s. Alright, so that's 30 minus 3s V naught plus 5s minus s squared V naught. Okay, it's going to equal 2 V naught minus 10. So let's try and bring like terms together. Taking 10 here is going to give us 40. So 40 plus 5s, okay, is going to equal 2 V naught plus 3s V naught plus s squared V naught. Okay. Okay, so now that we're done with this, the next step is to write our expression, in terms of V naught, since V naught is what we're trying to convert from s domain to time domain. Okay, so that's V naught s squared plus 3s plus 2. Making this subject a formula, you're going to have 40 plus 5s all over s squared plus 3s plus 2. And the next thing now is to solve for partial fractions, take the inverse Laplace. But you can tell from experience that this is very easily factorizable. Okay, so that's minus 1 minus 2. Right, so yeah, s plus 1, s plus 2. I can already see that this is much easier to solve with partial fractions. Okay, so you have 40 plus 5s so you have 40 plus 5s all over s plus 1, s plus 2, and that's going to be a over s plus 1 plus b over s plus 2. Multiply both sides by this denominator. You're going to have 40 plus 5s. You're going to be a into s plus 2 plus b into s plus 1. I know solving this is really, really hilarious. You just find the terms of s that will make this bracket 0 at one point, and this bracket 0 at another point, and that leaves you with another coefficient on its own. Okay, so let's start with this. So setting s to be minus 2. Okay, setting s being minus 2 will let this guy equal to 0, meaning we can solve for b. So when s is minus 2, we lose a entirely. So that's going to be 40 minus 10, that's 30. Is going to equal minus b. Okay, so b is equal to minus 30. It's as simple and straightforward as that. So when s is equal to minus 1, so now setting this equal to 0 so we can solve for a. Okay, you get 40 minus 5, so that's 35. Is going to equal a. So straightforward, we know that a is equal 35. So this guy is back in. We now know that v0 as a function of s is going to be 35 all over s plus 1 minus 30 into s plus 2. Okay? These are constants. Bringing them out and taking the inverse Laplace. We know that v0 as a function of time is the inverse Laplace of 35 over s plus 1 minus 30 over s plus 2. And these are just simple exponentials. So to wrap things up, v0 is a function of time is 35 e to the minus 1 times t. So that's e to the minus t. Then minus, since we have minus 30 here, 30 e to the minus 2t. Then we usually multiply this by u of t. All in both. So that's all that's there to solving, Laplace transforms with initial conditions. First of all, you understand how am I choosing to solve this? When the question, they told us to model inductors as a current source and capacitor as a voltage source. But if we wanted to do whatever, if we wanted to do it our own way, since we have these guys in parallel already, we could model this as a current source and also model this as a current source if we wanted to solve things as straightforwardly as possible. And if we wanted to go a bit extra, we could even source transform this, to something this way, and this will now become a current source. And you can see that the circuit will be much easier to solve. But we were told what to use in this question. That's why we did things the way we did. But in actuality, you can choose, except you're given, you can choose however you want to model this to make your solving as seamless as possible. So let's go to the last question for this. Okay. Assume v0 of 0, that's this, is equal to 5 volts. So this is the initial condition of the capacitor. Okay, it's the same as the last question, 5 volts. Which is included in the form of a current source. Okay, so now we were also still given how to model the capacitor in the S domain. So there's no free will here. You have to model this as a current source. Okay. Find v0 of t for t greater than 0. So what do we have here? This is our voltage source. 10 e to the minus t, u of t, simple transform. 10 ohm resistor, capacitor. We're modeling with a current source. Okay. And then our current source extending here is 2 dt. So this is the unit impulse function. Okay. The Laplace of the unit impulse function is 1. Okay, so we'll use this when we're solving. Use this when we're solving the questions. So we have to transform this into a circuit in the S domain. So we start with our voltage source, plus minus. Resistor stays the same. Okay, then a long chain of parallel elements. The second resistor, the capacitor, the current source that we're going to be using to model the capacitor, that points upwards for capacitors and downward for inductors, and then the external 2 dt amps. Okay, then we close our circuits. Then we start taking transforms. Now we have 10 e to the minus t. Okay, that's 10 over s plus 1. We've done this a million times. Okay, so 10 over s plus 1 resistors stay the same in the S domain, 10 to 10. This is our capacitor. We know that taking the Laplace of a capacitance is 1 over ST. Okay, so that since that's 0.1 farad, that's 1 over 10 farad, 10 over S. Okay, it usually helps to be careful with that, since most capacitances are in fractions. Okay, so we now know modeling capacitors as current sources. Okay, it's going to be in parallel with a current source going upwards. The value of that is going to be C times the initial voltage. Okay, or this remains 1 over SC. Your voltage as a function of S, and your capital I of S stays here. This would have been I of T, V of T, C for capacitance. Okay, so the most important thing we're looking at here is that this is the value of this is CV0. So our capacitance is 0.1, and our initial voltage is 5 volts. So that's going to be 0.5, sorry. Okay, 0.5. So we now know the value of this is 0.5 amps, and this is also 2 amps. Let's make this clear. Okay. .5 amps and this is 2 amps. So now you can also see that we have a lot of elements in parallel. We do have a lot of elements in parallel. So it's only going to make sense to do nodal analysis. Since you have current sources here, you can't particularly, do mesh analysis, since you can't really know the voltage across a current source. So nodal analysis over here is going to be our easiest way out of this. Okay, so let's start. Let's start with the solving. Okay, and then we're going to assign this guy a voltage of V0. Take this as a ground circuit, and we're going to draw a current flows. Since we have a source here, we're going to call I1 entering the node. All right, I2 leaving the node, I3 leaving the node. And since these two guys are sources, it's only safe to assume that they are entering the node, I5. You could combine these to 2.5 if you wanted to make your solving a little neater than average. But I don't see it doesn't affect much. Still the same mathematics you're doing. So we now know that I1 plus I4 plus I5 is going to equal I3 plus I4. Okay, simple and short. Let's start. Take the nodal analysis. It's initial minus final voltage all over the impedance. So that's 10 over S plus 1 minus V0 all over 10. Okay. I4 is plus 0.5 plus 3. So that's plus 2.5. It's going to equal I3, is going to be V0 divided by the resistance. Okay, so you're going to have V0 all over 10 over S. So that's S V0 over 10. Okay, so that's S V0 all over 10 plus, okay, this is for I3. And then for I2, that's just V0 over 10. Okay, we, as fast as possible, try to get rid of the denominator. So we're going to multiply this entire thing by 10. All right, so that's going to be 10 over S plus 1 minus V0 plus 2.5 plus 25, actually. Just multiply by 10 plus 25 is going to equal SV0 plus V0. Okay, keep in mind we're looking for whichever term we're solving for in the S domain, S0 or I0 usually. That's what we're trying to isolate. So once you see V0, don't even try getting distracted by adding this to this fraction. Just isolate it, take it to the other side. So you have 10 over S plus 1 plus 25. Okay, it's going to equal SV0 plus V0 plus another V0. Okay, so let's factorize that out. So it's going to be V0 into S plus 2. All right, we can now add these fractions. They don't have anything of importance to us. So 10 over, that's going to be 10 plus 25 S plus 25 all over s plus 1. Okay? 35 plus 25s all over s plus 1. And that's going to equal v naught into s plus 2. I hope you can now see where this is going, sort of. Taking this to the other side, so I still leave v naught. You now get a very simple and beautiful looking partial fraction expression. Okay? S plus 1, s plus 2. And now we can do what we do best to solve this. Okay? It's partition. Oops. Okay? So that's going to be a over s plus 1 plus b over s plus 2. Okay, you don't have to expand the brackets. The point of partial fractions is to factorize it as much as you can. So where you'd normally be tempted to multiply this out, just leave it that way. So we're going to clear the denominator here. So that's going to be 35 plus 25s. It's going to equal a into s plus 2 plus b into, s plus 1. And we're going to do the same thing we did for the last question. Okay? So setting s to be minus 2. Alright, so we're going to have a is going to tend to 0. So that's going to be 35 minus 50. Right? So what's 35 minus 50? I think that's minus 15. Okay, so that's minus 15. It's going to equal minus 2 plus 1. That's minus 1. So minus b. So we know that b is equal to 15. Cool. Setting s to be minus 1, so we can get rid of b. Okay, so that's going to be 35 minus 25. That's 10. So 10 is going to equal 2 minus 1. That's a. So straight up, 10 equals a, b equals 15. Throw these guys back into our original partial fraction. So we now know that v naught is always been a function of s, is a over s plus 1, right? So what's a? 10. 10 over s plus 1 plus 15 over s plus 2. Okay? v naught as a function of time is the inverse Laplace of v naught as a function of s. Obviously. So that's going to be the inverse Laplace of 10 over s plus 1 plus the inverse Laplace of 15 over s plus 2. Okay, if we bring out the numerators, this is going to be 1 over s plus 1, 1 over s plus 2, and a format we're familiar with. So that's just e to the minus whatever this value is. Okay, so finishing, v naught as a function of time, it's going to equal 10 e to the minus t. That doesn't look neat. 10 e to the minus t plus 15 e to the minus 2t e of t volts. And that's all we have to do. You can see we almost use the same format when solving for t less than 0 and t greater than 0. Okay, here they gave us how to model the capacitor, so there's no ambiguity. Okay, important thing is just to remember the values for the conversion. For the capacitor in parallel, it's going to be CV naught. Okay, so that's going to be your capacitor in parallel with a source going up. Okay, and this value of this is going to be CV naught. So it's important to remember the polarities of this and the values of this, because for inductors the current source goes down. Alright, so that's what we have to do when solving circuit problems with Laplace transform.